Yes, I appreciate the slow speaking to lead into me being ready. Thanks. All right. So, as is the traditional, greeting of our people, we've had AV problems. Thank you for your patience. Um, let's see if this thing works. If not, that's all right. Okay. Nope. Okay. So yes, I'm happy to be here. Yeah, feel free to do that in the meantime. Okay. So I'm Chris Martens. I'm faculty at Northeastern in Boston, and um, I'm excited to tell you a little about polarity and focusing. Um, sure. Yes. Yeah. This is the running joke of my life is that I have ADHD, so I have trouble focusing, and so I try to work on this topic to improve. Okay, so yeah, so if you were at Siva's talk yesterday, you heard a sort of version of some of my kind of the first half of my talk. It like sped up 4x. So if you heard Siva's talk and you were like, that sounds interesting, when I don't really follow or have any idea what this whole focusing thing is about. Hopefully this will help. Um, so life involves making choices, and so does proving theorems and writing programs. Okay, so if you're trying to prove a theorem, maybe you have some kind of view where you've got the things you've got in one window and the thing you're trying to prove in another, and you've got to prove R, and you've got a bunch of things around that you might use. So you've got some choice about whether you're going to take a look at what you want and then look back into your context of what you have and figure out how you might get it. Or on the other hand, you might take a look at what you have and notice you can combine them and maybe make some progress towards your goal. All right, now let's say you're writing a program. Maybe you're one of the other type of crowd I hang out with, and you like to write games. And you're thinking, I want to build a game or a game engine or something where there's going to be some way of processing user actions and or player actions, and it's going to update the world somehow. Okay, so if you're a particularly weird game designer, you'll think, I'll use a functional language and maybe I'll write a data type to represent my game world. And on the other hand, you're probably more likely to say, I should use like an object or something, and I'm going to kind of write like a signature that doesn't necessarily tell you how I'm directly updating my data structure, but it's going to give you a kind of a way to send messages, right, and see some updates. Okay, so these are all important choices we have to make. And polarity and focusing are proof theoretic techniques that maybe can help us make some of these choices, but at the very least, they'll help us understand the consequences of them. All right. Now, that whole picture might seem a little bit distant from something you might be a little more used to in this realm, which is the difference between values and computations. So you might have been told that values are things that have structure to them, like pairs and injections, and computations are things like functions and well, maybe lazy pairs that you could project out of. So values have some kind of observable structure to them, and they can be used by pattern matching on them, by sort of taking apart their components. And computations are opaque. Use them by providing arguments. This is sort of the view taken in call by push value, if you're familiar with that. So you might have also heard that these things might be referred to as positive, and the computations are negative. Okay, but so why exactly do we assign these polarities to the types associated with these values? Like, where does that idea come from? If you're adding a new construct into your language, how do you decide what polarity it is? How would you know? Okay, so this is where the proof theory can help. So these things have something to do with each other, is the idea. So the goals of this talk are, if sort of any of you don't yet feel initiated into the secret esoteric club of understanding polarity and focusing, this will be your initiation ritual, I hope. So I'd like to do something, I'd like to be kind of pedagogical about this, and if you have questions, sort of conceptual questions, I'd absolutely be delighted to field those. But I also want to try to recount some of the history and lineage of these ideas along the way. Um, and stop to kind of see the sights in terms of there's really cool work that's been done at this intersection for the last 20 years or so. And then I'd like to hopefully grapple with some persistent myths and misconceptions that sometimes sort of float around in when you get to talking about these things, and then maybe motivate some continued study. Sound good? Cool. Okay. So we're going to start in the world of proof search. That's sort of where I'm most comfortable. I sort of started liking logic and eventually learned that there were ways of using a computer that could have to do with logic. So this is where I like to start. And I'll say, so in proof search, it's really natural to use the sequent calculus because you can kind of always work in one direction. You can work from the bottom of the sequent, your goal, upwards. So the way you do that is you use the definitions of the connectives, which are given by inference rules, of right rules and left rules. And the right rules decompose connectives on the right, and the left rules decompose connectives on the left. So you keep on working, decomposing your formulas up the sequent. Some of these paths will fail, but if your sequent is provable, eventually you'll reach some proof tree where all the leaves are the identity axiom uh, uh, or the initial rule or the hypothesis rule. There's lots of names for it. Okay. So just for this presentation, we'll stick with a pretty kind of the minimal calculus we'll need to get across some of the important ideas. So we'll have base propositions P and unit and a conjunction or a product and an implication or a function type. So I'm going to be freely kind of talking across the props as types or Curry-Howard correspondence in this talk. So if so sometimes I'll pronounce one as truth and times as and arrow as implies. Hopefully that's not too unfamiliar for folks, but yeah, if you need to write this down in your copybook to refer to, this is the time. All right, so now let's work on an example. So it's a bit different from the one we started with. So we've got P and Q. We've got a way of turning Q and R into S, and we'd like to know if there's a way to turn R into S. Okay, so there's a lot of choices here right off the bat. There's a lot of rules in our little sequent calculus. There's the inference rules up in the corner. There's a lot of rules. So if I'm trying to prove this theorem, I'll look at my sequent. I'll look to the rules. I'll try to figure out what matches. Okay, well there's and left. I could decompose that. There's implication left. I could try using the implication in my context to have to provide it an argument, right? Or I could use implication right. So all these things are seemingly applicable. Okay, well, if we try right away to do implication left, we'll fail, right? Because we need to show the antecedent Q and R, and we don't have the ability to do that from the context that's given. So that proof will fail. Here's one that succeeds. So we'll first get R into our context, and then we'll break apart P and Q, and then we'll build up the antecedent, and we'll apply the function. Right? That one works. Okay, there's another one that also works. This one I think is just swapping around whether we're doing the implication left or the and left first, right? So this one works. Okay, well, so great. I found one that works. Maybe I could have tried doing something smarter, done these things in a different order. And also, if I found two proofs, is there one of them that's somehow better than the other? Is there kind of a sense in which I prefer one over the other? Okay. Well, so one of the reasons people care about proof search is in the context of logic programming. So there's this paradigm, sort of outside of props as types. There's also propositions as programs. And in that model, you run your program by executing proof search. So you can interpret a little like a Prolog or Datalog program. If the syntax is familiar to you, you can translate it into a sequent and then say, okay, give me a proof of that sequent, and that will be an answer to my logic program. And this was the context that Jean-Marc Andreoli was working in 1992. Specifically, he was interested in using linear logic as a logic programming language. And he was interested in okay, well, we've got all this non-determinism in proof search. How do we cut that down? There's an efficiency question there, but also just kind of a practical question from a programming standpoint. You maybe want your programming language to be deterministic. So just realized my slides are being covered up. Okay. Move this somewhere.
Let's look at the chat as well.
I do not have to leave. If I look at the chat, everything will go wrong. Someone else can look at the chat and tell me if there's anything important. Okay? Good. Thanks. Great. Okay. Okay, so Andrew really made this observation. Some rules are invertible. Okay, what does invertible mean? Simply that the conclusion implies the premise, right? So you're usually used to thinking inference rules means if you have all the premises, then you have the conclusion. So invertible means if you know the conclusion, you can prove all the premises, sort of admissibly, right? So you can prove a rule is invertible by assuming you have a derivation of the conclusion and then proving that you can derive the premises. So that's the case for and left, right? So that one's invertible. Have I lost my mouse? Is this a mouse focus problem? So many focusing jokes. Okay, great. All right, so with these invertible rules, right, there's some sense, intuitively at least, that it should always be safe to apply them, right? There's kind of no risk. And what's the risk? Well, okay, there's no risk of backtracking. Okay, you'll always be able to do this sort of eagerly. So here's a non-invertible rule, the implication left rule. Remember, this one was the one that got us into trouble in that initial proof. So why was that? Well, because when you're using an implication, you've got to come up with the argument, and that's not really a sure thing, right? That's another thing you've got to prove. So this one's not invertible. We have to make important choices. You have to choose, one of the functions that's going to actually work. Okay. So and really said, all right, let's try two things. The first one is we're going to apply invertible rules eagerly. We're just going to do it all at once and as much as we can. And then when we decide to try something, one of these important decisions, we're going to stick to it. We're going to hard commit. Okay, what does that mean? Well, if we look at this example, so if we decide we're going to decompose A implies B, then what we're going to do is we're going to maintain focus. So we're going to say we're going to focus on A implies B. This is a left focus because it's to the left of the turnstile. And then we're going to maintain focus on the subformulas. So for the first premise, we'll shift into right focus on the thing we need to provide to the arrow. And then on the other premise, we'll focus on the left, on the thing we get out as a result. So this is the strategy of focusing. It's a proof search strategy where first you imply all of your invertible rules that you can, both on the left and on the right. That's your inversion phase. Then you pick a formula to focus on. That's the focus phase. There's still some non-determinism there, right? There's not a claim this removes all non-determinism, but yeah, okay. So you pick one, and then whenever you pick it, you continue applying these non-invertible rules to the subformulas until none of them apply, and then you shift back into this inversion phase, right? So it shifts proof search into these two kind of neatly organized phases. So the surprising result of all of this is that the strategy is actually complete. It's also sound, but maybe that's not so surprising because all you're doing is restricting your use of the sequent rules to, a particular, using particular ones at particular times. Yes?
Why is it a good idea to keep focusing on the one thing until you don't do anything with it anymore, rather than going directly back to unfocused and doing your invertible thing?
Right. Yeah. So why is it a good idea? So are you asking why does that maintain completeness, or why does that help with the non-determinism aspect of it? Yeah, so it helps with non-determinism because you only ever have one thing to do, right? You always know exactly what the next step is. But except for these very particular points where you're moving between inversion and focus, right? So that's why it's a good idea. It's complete. Well, the reason it's complete is the surprising part, right? And that's the part that's, you have to do a complicated proof to show it. Yeah, I won't really get into the proof techniques in this talk. I'd have to honestly recall them personally, but I can certainly, there's actually a really nice paper that gives a really nice proof of it that I can send you if you're curious.
So the point is that you're kind of cutting the search space more by saying once you focus on this thing, you just stay on it.
Yeah, exactly. Yep. Thanks. Yep.
That's really backtracking for the.
Who's speaking? Sorry, I can't quite see. Oh, yes.
Focus phase, I guess you're backtracking. If you focus on the wrong thing, then you
Right, and so you'd have to backtrack to that choice point, right? But not necessarily to, you wouldn't need to backtrack over the inversion part, right? That's kind of the key. Yeah. Great. So again, let's do an example. So this was the formula from before. Okay, well, actually, now I'll ask you. So this was the part where I said we've got, we had several choices before. So, well, what do you think we should do first? Deconstruct the pair. That's one correct answer. Is there a second correct answer? Yes? Implication right, yeah. Okay, so I didn't tell the whole story with inversion. It actually doesn't matter. You could do them in either order, but sort of arbitrarily, we want to, again, if we're cutting down non-determinism, we want to pick one side to kind of do first. So we'll do right inversion first. That means we'll put the R in the context. And then, yes, there's still inversion to do. So we'll break down the pair. Great. Or this is our inversion phase. That's done. Yeah, so this is the end of the inversion phase. And now the sequent is something, it's helpful to give a name to this state, which is stability. So the sequent is stable at this point. There's no more inversion to be done. And now we've got to make a choice. Well, yeah.
Invert those first,
Yes.
but you didn't put it. Because you could have done this, the splitting product first, no?
Yeah. So both of these rules are invertible. Yeah, so you can do them in either order, but we're choosing right inversion first. Yeah, it's all good. Yeah, great. Okay, so we reach a stable sequent and then we focus. So, okay, in this case, there's only one real choice, but okay, so we focus. We say we're going to focus on Q and R implies S. That means we've got to maintain focus on Q, proving Q and R, and then we'll keep focus on the thing we get out and continue. So, yes?
You select E.
Yeah, okay, good question. This will hopefully become clearer at some point what to do with the propositional atoms. Yeah, so I mean, basically, if you did, you would fail, right? That's the short answer. We'll have a sort of more satisfying answer. Yeah. So there's fiddly details about how you might do this in practice, but yeah, essentially, when you have to make a choice, right? There may be potentially several choices. Yeah.
So the focusing is only for the non-invertible rule, but here you also focus when you apply the invertible rule.
No, that's not. So sorry, my notation may be a little confusing. So I'm using underline just to indicate the formula that I'm doing the rule on. But the focus brackets are, yeah, the focusing is the brackets. Yeah, thanks for the clarification. Yep, got it. Okay, all right, so let's finish this proof, right? Or are we almost done? Okay, so this will go by fast, but all right, so we focus on all the pieces and then we can satisfy with ID. Great. Any questions now? This is a good point to ask clarifying questions. Yes.
Maybe I misremembered what the sort of algorithm was, but we have that we keep applying non-invertible rules to the focus things. Oh wait, the times are non-invertible. Yeah, so good question. You're catching a subtlety here. So I didn't go through all the rules and categorize which ones are invertible and not. And intuitionistically, in this sequent calculus, it is invertible on the right. We're going to pretend right now that it's not. We could still do this proof. There would just be a step. Actually, let me give you another example, and I'll show you sort of what you do when you're focused on something that then you can't apply non-invertible rules to anymore. Okay, thanks. But yeah, thanks. This question in the back? Can we like, I don't want to make you run. Can we like pass it? This is, oh dear, okay. Okay, yeah, while we're waiting for this, if you want to work one on your own, try this one. Yeah, I was wondering when you're checking for the axiom, because presumably doing it every step is too expensive.
Yeah, so when are you checking for the axiom? Well, this is related to the question of can you focus on just an atomic proposition in the context, right? So you will need to do that sometimes. You'll also be focused on an atomic proposition on the right sometimes, and then you'd need to check whether it's in the context. So we'll actually have multiple different ID rules in the end, but we don't quite have what we need yet in order to make that idea precise. So yeah, thanks. Anything else? Awesome. Okay, so maybe you've played along a little, so now we can look at this one. All right, so we've got P to Q, we've got P and R. We want to show Q and R. So we'll
do the right inversion to get all the arguments into our context. We'll do left inversion to break apart the P and R. Then we'll left focus on P implies Q. We'll focus on P and see that we have it in our context. We'll focus on Q on the left. And this is where we'll actually need to blur. Okay, so we focus on Q on the left, and there's not a way we can immediately succeed. So we'll say, okay, we'll drop focus. Okay, so now we'll drop focus and we'll try going back into the inversion phase. So we'll draw focus on Q. That's what this rule I haven't told you about yet, called blur. Okay, so we blur, and then we can choose to focus on the and on the right. And if we do that, we've maintained focus on the subformulas on either side, and we can succeed because what we need is in the context. Okay. So that's the basic idea. And when we do this, what we see is that a focused proof is a kind of normal form for sequent proofs, right? In the same way as a sort of a normal form for a lambda term. So that's a property. So like a focused is a property of proofs, but it's also, we also want to talk about focused proof systems, right? So one which yields focused proofs by construction. Am I already at?
The audio through Zoom is muted, so.
Oh, am I not being picked up by another microphone for Zoom?
I'm not sure. You can mute. You can leave it muted? Okay.
It's okay? All right, thank you. Okay. I am running behind schedule though, so let me, yeah. No, that's okay. Yeah, I just want to, will I get a few more minutes since I started late, or should I still try to wrap up it? Yeah, okay, great. Okay, so we want to get from a focused sequent calculus to, or sorry, from focused proofs to a, I'm getting echo? No, okay, to a focused sequent calculus. So this is where we go ahead and notice that, all right, well, we've got a lot of these connectives that are actually in both, so we've got an invertible left rule for and unit, but we've got invertible right rules for all of them, and the actually and implies left is the only one that technically in this system does not have an invertible left rule. So what we do now is we look at linear logic, and we notice actually this clarifies things to an extent because we can stratify all the propositions, and we can notice that we can divide them into the ones that have invertible left rules and invertible right rules. And we can call these positive and negative. So this is like the definition of polarity. This is where it comes from, is whether the connective is invertible on the left or on the right. Okay. So once we've got this idea in mind, we can give ourselves a more kind of, we can refine our syntax. We can first of all just say, well, all right, look at all of our propositions, and now we can kind of categorize them as positive or negative, at least in terms of their outermost constructor. That's what this grammar will do. But we can go even further with that, and we can say we want it to be completely unambiguous what polarity something is, so that, again, less non-determinism. There's only a certain number of rules we can apply, and we can kind of soundly treat each of these as a certain polarity. We can take a tip from linear logic, and we can notice we now have two conjunctions. We have a positive conjunction and a negative one, depending on what our depending on what our left rule is. Yeah, if you have the, I'm thinking in natural deduction now, but depending on whether you have the projections or you split your conjunction into variables. Okay. So in order to get this to work, and in order to still have all of the propositions we want, we've also got to add these annotations, these shifts between propositions. Okay, so what this means is that for a given proposition in an unfocused system, if we want to sort of translate that and get a proof for it in a focused system, we've got to explicitly polarize everything. And this is where some of these questions about what do we do with the atomic propositions come out, right? We've got to pick a polarization strategy. So in this example, I've arbitrarily chosen to assign P and R positive polarity and Q negative polarity. One can choose to do it really however you want. The focusing strategy is complete no matter what. But it's common, I think, to, I'll say that in a minute. So you've got to polarize all your atoms, and then you've got to add in shift operators everywhere, right? So for an implication, we've got to have positive things to the left of the arrow, and then we've got to have a negative thing to the right. So we'll use the shift to turn negative, the downshift to turn negative things into positives, and the upshift to turn positives into negatives. It's backwards to my brain. Don't worry if it is for yours, but that's how it is in most of the literature on this. Okay, so we've got to insert shifts, and we've got to choose this polarity, this polarization strategy, and it's sort of common to use all positive, but again, that isn't a requirement. So we can turn all of this into a focused sequent calculus by basically setting up all these judgments that correspond to the different phases of focusing. So we've got a right focus phase, we've got a positive thing on the right, a left focus phase where we have a negative thing on the left, and then the other two options are inversion. And for the inversion phases, we're adding this second context, omega, which is actually ordered. So we're going to put things, it's where we're going to like sort of put things in when we're doing implication, right? Kind of inverting things into left. And then we're going to get a bunch of positive things in that context. So we're going to decompose them. And then we're going to occasionally move one of those things into the regular gamma context when it's negative, right? When it represents a choice we might have to make in one of the focusing phases. Okay, so mostly the job then is to sort of categorize all of our rules, our left and right rules for the connectives into one of these four judgments and sort of write them in such a way that it makes sense. But we've also got to introduce these rules for moving between the phases. So we've got the blurring rules on both sides of the sequent. We've got the focusing rules, which only apply, right? Again, reading these rules from bottom up, which you always want to do with sequent calculus. We say these rules only apply when our inversion context is empty. So as soon as we're done, that's how we know we're done with inversion, right? When we're done with inversion, we can focus on the right or focus on the left, on the right on something positive or on the left on something negative. Okay, so this is how all of the rules fit into each of these categories. Hopefully nothing too confusing. This might be a good slide to take a picture of if you want to reference it for the later bits. I'll pause for a moment. Okay. Yeah, and so this is a focused proof of, what was this? I think this was the sequence from the beginning. I won't go through this one. Exercise to the reader, go back to that original sequence and do it in terms of the focusing rules. So, all right, so I've given you a lot of proof theory, a lot of inference rules, and you might be wondering, all right, well, like when do I get to write a program? Some of you in the room anyway might be wondering this. And now I'll talk a little about programming. So I like two kinds of programming. Okay, I like more than that, but for the purpose of this talk, I like two kinds of programming: logic programming and lambda calculus-based programming, functional programming, what have you. So we can give two answers to this. So Andreoli's original context was logic programming, and in logic programming, we've got this model of proof search as computation, and there's sort of two presiding models of logic programming. You've got forward chaining and backward chaining. So for forward chaining, think data log. For backward chaining, think prolog. This is the the hello world or the length index vectors for dependent types of logic programming, which is the transitive path relation. Computing a path from a bunch of edge facts, okay? And so this is like a standard sort of data log program where you'd say, okay, I've got a bunch of edge facts and I'm just going to churn out everything I can learn from those facts to generate the sort of full representation of reachability in my graph. And maybe that I could query it after the fact. But I'm basically going to eagerly apply everything forward. And then in the prolog side, you usually have, maybe for the same program, you've got sort of a query interface where you say, I would like to know whether there's specifically a path between A and B, and only on the basis of that information will I do proof search to figure out whether that's true. So this is not like one of these is better than the other or something, but these are two common ways of doing it. Okay, and so it turns out you get these different modes of logic programming. For forward chaining, if you choose a polarization strategy so that all your atoms are positive, and you get backward chaining if you polarize all your atoms negative. Basically what this means is that when you do this, like the backward chaining search will fail for the first strategy. The forward chaining search will fail for the second strategy. And it's interesting to look at, like, I mean, the proof will succeed in both cases, but you'll sort of fail and have to backtrack first. So it's interesting to see why. Ask me afterwards if you want me to show you on paper how this works. There's a nice paper about it, which I meant to add to the slide, but yeah. That's Chowdhury and Fenning, maybe Chowdhury and Miller. Yeah, I'll get it later. Okay. So the second sort of thing of interest here, maybe more to this crowd, is lambda calculi, in which we have computation as proof reduction, right? The sort of computation in this setting on the other side of Curry-Howard can be seen as we have like circularities in proofs. Oh, I don't have that slide here. Okay, we've got like circularities in proofs, and then we're reducing them until we get to a normal form. So in this case, we will want to do like a proof term assignment for our focus sequent calculus. And when we do this, we'll see, for example, that we get different proof terms. If we use different proof terms for our positive and negative pairs, then we'll have, as predicted, as foretold, we'll use a negative pair by projecting. This is the kind of sending a message, and then we'll use the value version, or the this is like the computational pair, right? And this is the value pair, and a value pair is something we can pattern match. Right, and so also operationally, you'll find that in a polarized system, the negative pair has a lazy evaluation strategy, and the eager pair has an eager one. Okay, positive pair has an eager one. Okay, so the proof term assignment looks something like this. So for the right inversion phase, we'll have values of positive type. Think this is your pairs and units, and this is your like polynomial functor, strictly positive data structures. Then you've got spines, or I think this might be the same as what Celia yesterday was calling stacks. But anyway, this is the left inversion phase, where you've got something on the left you're focusing on. So you think of this as something where you're like the proposition of interest is on the left, and then you've got something more you're doing with it. So you go forward. You've got things like terms, which are kind of like, you might say these are sort of your computation terms. These are your negative sort of inversion on the right. And then you've got patterns on the left, and patterns are actually what we think of as patterns in functional programming. Okay, so this is one cool thing about it. Here's an example. This is the polarized version of that example we had before. We've got a function from P to Q. We've got a pair of P and R, and we can show we've got a pair of Q and R. I think that's the same one. That might be slightly different. Sorry. And okay, so then we can lambda abstract. We can take our big pile of inference rules that we stack together into a proof and write it as a nice compact lambda term, where we'll bind. So lambdas now don't just bind variables; they bind patterns. Okay, so this curly brace syntax is actually a pattern for the like upshift, the downshift, right? The inclusion of negatives into positives, right? Because everything bound by lambda has to be positive, but this is a function, so it's got to be shifted. And that shift is represented by the curly braces as a pattern. Likewise, the pair has a familiar pair pattern syntax, and it's, the rest of them look like what you are familiar with. Our matches also match over patterns, and our matches match on computations, but then the cases before the arrows are patterns. I have some useful things here. Okay, so lambdas bind patterns, as do matches. And functions have to be, this is the other bit, functions have to be fully applied. So the syntax with the dot in it indicates that this thing to the right of F is actually a spine, which is to say a list of arguments. So it's got to be fully applied and therefore eta expanded. And this sort of match and then return syntax might remind you of like a monadic bind or sequencing. We see this in call by push value too. Okay. So for more detail about this idea, and specifically this tight correspondence with pattern matching, you should take a look at, the pattern matching thing in particular is Krishnaswamy 2009. It's a really nice account. It's just about the kind of like how focusing really naturally, logically explains pattern matching in functional languages. But the version I showed here is actually closest to Dunfield and Krishnaswamy's bidirectional typing paper from 2021, which is sort of a survey, but really nice presentation. And and then Noam Zeilberger's dissertation in 2009 was the logical basis of pattern matching and evaluation order. It was about all these things, but done in a classical calculus, so it's harder for my brain to make sense of. And then Simmons 2014, this was this is also the account of the best presentation of the proof that I know of for the completeness of focusing. It's called structural focalization, and it also gives a really sort of complete and I think fairly readable account of proof terms for the fully focused system. There's a whole section with lots of examples that are like, here's a focused proof term, and here's how you might write that in like an ML family language. Okay. Right, so a lot of this was developed in this context of dependent types for logical frameworks. Okay, I'll skip this slide, but ask me about it later. See, I'm running low on time. Okay, so programmers like to cause problems on purpose, and by problems, I mean introduce redexes. That's how we write programs. So we've got to actually do this process of going to normal forms. And we'll usually do this in a sequent calculus presentation by thinking of these redexes as cuts, right? As okay, I've got a proof of A, I've got something that relies on a proof of A to get a proof of B. Now I'll use the cut rule to put those together. We can give a proof term assignment, usually written with a let expression to cut. And then we get this interesting kind of this level of Curry-Howard, which is actually a meta-theoretic proof, right? The cut admissibility proof for a sequent calculus shows how it goes through all the cases of where you might have a cut and shows you can eliminate those cuts to show that the cut rule is admissible and therefore not really necessary to include in a logic to show it's sound. The standard soundness result translates into an operational semantics. Okay. All right. So points of frequent confusion and conflation. All right, okay, I wish I had more time to talk about this part because it's the fun part. All right, this will be, talk to me in the hallway later. So there's a bunch of things here. I don't have the knowledge to tell you about all of these relationships, but I can tell you about these ones. And in particular, there's been some like work after a bunch of people were doing all of this stuff that really did a nice job of elucidating some of these ideas. And there's one that I think that I'm working on at the moment, which is kind of clarifying this relationship. Adjoint logic, think LNL, if you know what that is. Okay. So one of them is this point that bidirectional typing is not actually directly the computational content of polarized logic. Jana Dunfield and Neil Krishnaswamy have this lovely line. A widespread folklore belief among researchers is that bidirectional typing arises from polarized formulations of logic. This belief is natural, helpful, and wrong. Okay, I won't go through this. But so basically they motivate the use of polarity in a bidirectional type system, but they kind of describe it as optional. So they'll say this is like what it has in common is this idea of kind of characterizing beta eta equality, but it doesn't. But yeah, this idea of explicitly polarizing your calculus using these shifts operators is not necessary for bidirectional typing. Okay, get the picture of that. Okay, but they also do this, right? They conflate these things. They say polarized type theory, focalization, or call by push value, variously called, right? This kind of is like, whatever, all these things. So the second point of confusion is that polarity and focusing aren't really the same thing. Okay, so actually, I'm using these terms a little differently from the literature. By polarity, I actually mean something closer to call by push value. What I mean is computation value separation with explicit shifts in the types. Okay, so if you do this explicit separation, this is what I call a polarized type system. And a focused type system is one that has this sort of beta eta length property. And obviously, so those are not the same thing. Hausbrock-Nanestad's paper in PPDP 2015, I think, has a really nice discussion of this, starting with the really lovely observation that these things are actually double discoveries. Levy didn't know about polarized or focused sequent calculus stuff. At the time, and he visited CMU in 2009 when I was a baby grad student and had all these fiery conversations where they were like, are we doing the same thing or not? And it turns out they were in some ways, but not in others. Nonetheless, their convergence is a sign of their significance. Okay, let me skip to the end. Okay. We can talk about those things if you want in the hall. So there's some life lessons, I think, we could learn. Life involves making choices too. So when you're struggling to focus on what matters, I think it's a good idea to make the easy choices before the difficult ones. That's something I have to remind myself of a lot. It's okay to do just one thing at a time, maybe even a good idea. And if you get stuck trying to reach your goal, then try taking a closer look at what you already have. That might be helpful. And I think convergence is sometimes a sign of significance. That's always very exciting, but you do have to look carefully at the fine print. So, all right, there's still more to do. I'm interested in all of these things. Maybe language implementation is the one I think would be most impactful, but at the moment, just like intellectually, I'm kind of more interested in the first one, the second one, and the pedagogy one. I think there's some interesting stuff to do with like teaching proofs that could come out of this. So talk to me if you're interested in any of these things. And there's some information. If you go to that URL, you'll also find my Google Doc with a bibliography for all these things. And I'm certainly missing some things. So I've turned on the ability to make suggestions and comments on that Google Doc. If you know of references I've missed, please go ahead and add them. I'll end there.